All right, so this is part two, I guess, and I'm gonna go over this document as well. I'm not gonna write down anything because I'm kind of lazy, but I wanted to record that video still. And we're still looking at the range proof. If you haven't seen the previous one, just as a recap, we're trying to check that the value is in some range, value v, but we only have a commitment to it, and the commitment is blinding. So we have a blinding factor, and to check that, we're basically checking that we have a binary decomposition where the A vector, which is letter called AL, represents the bits of V. And we also need to prove that AL represents the bits, not only the binary decomposition of size n. And to do that, we create this other variable called AR, which represents AL minus 1. And we prove that AL minus 1 times AL equals 0, where we have the Hadamard products, and so 0 is a vector, meaning that everything is 0 or 1. All right, if you don't know that, just watch the first video. And what we ended up doing is that we sort of build that circuit where we have already an inner product, which is here, L times R, where this is the left side and the right side, so a single inner product, and this is the result. And the result is basically some delta function that is computed by the verifier because it's only based on verifier challenges, something the verifier knows. And here we have the value V, so this will be a commitment. And on the other side, this is something that called L and R that will also be computable by the verifier. And we initially said that things are unblinded. So AL is a witness value because it contains the bits of V. So we're revealing stuff, and the output also reveals V. So we want to blind things. You can try to understand the protocol without the blinding part, but I'm going to explain the blinding part now. And so to do that, basically, we're seeing these things as polynomials, where these are going to be the constant terms. And then, so L0 and R0, that's what we're going to call them. And then we're going to add some random value here times X. So the random value here is SL, and the random value here is SR. And basically, if we don't move them into this X here, it's kind of hard to figure out that to recover the output. So we can blind stuff by just randomizing things kind of in a brute force way, but then it's kind of hard to, if we do an inner product on that and that, it's kind of hard to actually get the output. So what we're doing is that we're sort of shifting the blinding factors with this X, these polynomials, right? And so it makes it so when we do the inner product, we're going to get a new polynomial T, which is going to be this polynomial of degree 2, because we have multiplication between two polynomial of degree 1. And the constant term is going to be what we expect, this L0, R0, which is what we expected here. Okay? So that's sort of how we're going to recover the output. So, of course, we don't know how to do inner products of polynomials. So what we're going to do is that we're going to evaluate this L, this R, and this T at some challenge point X. And so if you're familiar with these kind of tricks in proof systems, this is basically a Schwarz-Zippel lemma kind of trick where we prove that this is true for this identity, or this inner product is true for these polynomials L, R, and T. But we prove that by just proving it at some evaluation X for an instantiation of X. So we really have numbers. And if this is true at X, then this is true, most likely true all of the time. Okay, so there's two things here. Basically, there's how does the verifier creates these inputs to the inner product. The inner product, you can look at it, I'm not going to explain it here. You can see it as a black box. It takes some inputs and some output T. And it expects you to give that to them as commitments. And so we just need to figure out how do we create these things here, and then how do we, the prover will give us T, but how do we extract the output, which is in T0 from T. And so there's two sections. Proving that T0 is correct is basically extracting the output of T, and proving that L of X and R of X are correct is basically computing as the verifier the left input and right input instantiated at this point X. So these are blinded inputs to give to the IPA. Again, the prover will give us the output to give to the IPA, but as the verifier, we can compute the inputs. Okay, so we have this nice diagram here, which is a bit complicated to understand the first time you look at it. But basically, it says that this is the input that we're going to give to the IPA. Actually, this is the blinded input that we don't want to give a blinded input to the IPA, so we'll have to remove this thing here. But before I tell you how to remove the blinding, we can just look at that and see that this is the L of X. So this is a point, right? Not a vector. It's evaluated at some X, which is a challenge given to us by the verifier, times the base G. So this is a multi-exponentiation, or here multi-scalar multiplication. And here, strangely, we get R of X times H prime. And so we're going to see why we're not using H and we're using H prime. But the reason is explained. Where is it explained? I mean, we can try to use H and sort of see where that we get stuck. But if we look at things, basically, you're going to see that H prime is something that the verifier knows. Here's a challenge that we used previously, times H. So it's just, we're kind of sort of shifting the base here. And we're really doing that because otherwise it's kind of difficult to get something times H. Okay, how do we build that? How do we build these inputs? We take this thing here. So this is the commitment to AL and AR that we got from the prover. So this is really one commitment. AL committed with the base G, AR committed with the base H, and this is the blinding factors, A with the blinding base. So this is how we blind these commitments. And here we get the S is a commitment to these blinding factors. So we have to sort of reveal the blinding factors. We have to add the blinding factors, but we don't reveal it because we blind this. So we have this S tilde, which allows us to blind this value. And here we add all of the stuff that we need to add so that we have all of the public stuff. Right? So we can look at it, but if we look at the L that we were expecting here, it's AL minus Z1. And that was the unblinded one. The blinded was AL plus this blinding stuff minus Z1. We can look at it. Back here, AL plus XSL minus Z1, right? This is what we're expecting. It's all multiplied to the base G. And for R, we're expecting this thing here, YN is a Hadamard product of this stuff, right? And so AR, but it's not times YN, right? You notice that? Plus SR, not times YN as well, plus all that bullshit stuff that we're adding here. And that's where the magic happens, right? Since it's this base is yn minus 1 times h, it means that h is yn Hadamard product of h prime. So that's why this thing here is basically equal to, you can see it as AR times, do we write it anywhere here? Maybe not. You can see this as AR times yn Hadamard product h prime. Or AR Hadamard product yn, not yn minus n here, if we put it on the left-hand side, AR Hadamard product yn times h prime, or inner product with h prime. So that's just how we can see these bases. So I recap, we add this commitment that we already had in the protocol of the left AL and AR, hiding commitment, right? We add the hiding commitment to these two blinding factor. multiply by x. This is our evaluation points. And then we add a bunch of stuff. This is a big point, right? Which we can compute ourselves. And then we're gonna do minus this thing here, um, which can be you can see here minus this thing here, so that we get this non-hiding commitment here. And this thing here is is an addition of two different blinding factors. So the prover, I believe the prover sends that to us, and it's all good. Okay, so if that made sense, like let's look at how we give that to the inner product, right? We give this P, which is all of these things minus this blinding stuff to remove the blinding factor. And then we give it to the inner product, we give it with T of X, which the prover has given to us. Now we need to, and the inner product is going to tell us if it's true or not, okay? So now we need to look at this output, and we need to prove that it's equal to the stuff that we expected, right? Or this was the unblinded stuff, the blinding stuff. The blinded one is a T of X, where the constant term is correctly formed, and then we have some garbage in the X and X square as coefficients. And what we can do is that the prover has sent us a commitment to the coefficients, so it becomes very easy, T1 and T2. We can evaluate T at X by basically taking the constant factor, or at least the constant factor, the constant coefficient which we're expecting. So this is the output of the circuit. We're expecting that to be the constant coefficient, plus X times the commitment to T1, plus X squared times the commitment to T2. So these are basically, we're evaluating the polynomial T, given that we know the clear commitment, or we think we know it, and we know the coefficients for X and X squared. So we're evaluating it at X. It's supposed to give us a blinding opening of T of X. And good thing, the prover gave us this opening. They gave us T of X and the blinding factor here, which if you want to see how the prover computes that, basically the blinding is the combination of all the blinding factors of all the commitments that we're using, right? And this is it. This is sort of how we, they might say that it's proving that T here is correct, but you can also see it as extracting the constant coefficient, which is supposed to be the non-blinded result, the unblinded result from the blinded result. Cool. That's all I wanted to explain. And yeah, if you need more, just ask me and I'll do another video.